Assalamualaikum warahmatullahi wabarakatuh. My name is Shaila binti Azman. I would like to present about my FYP report, which is a study of onset on Bénard-Marangoni convection with internet heat generation. Chapter 1 Introduction. Background of the study. Convection is a form of energy distribution process that occurs in a fluid. There are two types of convection. First, forced convection occurs when a pump or other device moves the heated fluid. The second one is natural convection. It's the process of convection which occurs only through a change in density. Convection in the fluid layer. First is Bénard's convection, the convection phenomenon caused by the buoyancy, and the second one is Marangoni convection, the convection resulting from surface tension or thermocapillary force. For the problem statement, this analysis predicts that the onset of convection in a warmer liquid layer is more stable than the cooler due to internal heat generation. Therefore, this study seeks to resolve the onset of the Bénard-Marangoni convection caused by internal heat generation by rewriting the mathematical formula for the solution. For objective of the study, to get the analytical solution on the onset of Bénard-Marangoni convection generated by the generation of internal heat using the classical linear stability theory. Chapter 2 Literature Review. Past research. First, Bénard 1900 concludes that convection was due to buoyancy. Second one is Rayleigh 1916 was the first to analyze Bénard's theoretical formulation limited to two horizontal plates. And the third one is Bloch 1956 concluded that this phenomenon was due to the thermocapillary effect on the free surface rather than the buoyancy force. And for the highlight, the experiment conducted by Bénard 1900 and Bloch 1956 who contributed to the development of the science of fluid mechanics. For the theoretical studies, this study was motivated by a short-wave asymptotic analysis of Marangoni oscillation with internal heat generation by Hashim 2001. In this study, the one-layer fluid model will be used. Chapter 3 Mathematical Modeling. This is the figure 3.1 physical model of fluid layers. This study developed the mathematical modeling based on the one-layer fluid model as shown in figure 3.1. At the very beginning, the temperature complies with Newton's law of cooling in the form this question. Governing equation. To get the governing equation, this study used the Bosniak approach. Basic for approximation Bosniak is that all fluid properties are believed to be constant except for a change in density in vertical direction towards temperature. However, this approach can only be used in the event of a change in temperature is small. For the continuity equation is proposed by Anderson 1995. Momentum equation also based on Anderson 1995 and the energy equation is given by Char and Chiang 1994. For bottom surface boundary conditions, there are three boundary conditions considered on the solid surface Z equal to 0. That is non-slip condition, condition for continuity, and the last one is the condition of fluid which is close to a solid boundary of constant value of C. Free surface boundary conditions. At the free surface boundary Z equal to D, the three boundary conditions considered are kinematic condition, condition of continuity of normal stress, and the condition of continuity of shear stress. Normal and shear stress is the force applied to the normal and tangent fluid area. Stationary condition. At rest condition and without interruption, V equal to 0 and the free surface is flat. This is the hydrostatic pressure equation. Then we have linear equation. This is the momentum equation. This is the linear momentum equation and the linear energy equation. Bottom surface boundary conditions. Condition on rigid boundaries that was linearized are non-slip condition and a continuous condition to be considered in a vertical direction. For free surface boundary condition on rigid boundaries that was linearized are: first, kinematic condition; second, shear stress constant conditions; third is normal stress continuity conditions; and the fourth is Newton's law of cooling. Next, we have to analyze the normal mode. Dimensionless governing equations and boundary condition produce 7 quantities non-dimensional as shown in table 3.1. The study rejected the dimensions of the equation. Then we have the momentum equation. Same goes to energy equation. Okay, for the bottom surface boundary condition, there are 3 conditions, which are: the terms are not slip for equations, conditions for continuity for equation, and the third one is temperature condition for equations. Next one is the free surface boundary conditions, which have 4 conditions: kinematic conditions, shear stress constant conditions, normal stress continuity conditions, and Newton's law of cooling. And the last one is dimensionless linear equation, where the bottom boundary layer is conducive to heat perfectly by internal heat generation factor. The theoretical study described above explains the inconsistencies between the effects of the buoyancy force and the applied voltage surface, each represented by Rayleigh number and Marangoni number. However, in an experiment, the parameters that control fluid phenomena are the difference in temperature across the fluid layer. These differences give rise to a linear relationship between R and M. For Chapter 4 Result and Discussion, Figure 4.1 shows the velocity curve of the main order fluid. It is found that fluid velocity increasing with depth and decreases sharply when very close to the surface of the fluid. This phenomena is only a temporary effect of fluid velocity in this stage. Figure 4.2 shows the temperature influenced by the heat generating factor, which is depth increases as it crosses the depth. The increase in temperature is more pronounced when the number of waves increase. Figure 4.3a and b, it showed a higher temperature rise when the value of the internal heat source increased. This phenomenon shows that the internal heat generating factor influences the change in fluid density depending on the change in temperature. This, in turn, is going to further accelerate system instability. Figure 4.4 shows that the system is easily influenced by an internal heat generating factor. Figure 4.5 shows that the value increase Q will affect the value R naught when the value PR increases. Figure 4.6. This result is the same as the result Hisham 2001, which also ignores the effects of gravity. This indicates that gravity effects influence convection phenomena. Chapter 5, Conclusion and Recommendation. From the analysis carried out, this study summarizes 3 important solutions to the problems of this main order. The internal heat source does not affect fluid velocity but has a clear effect on fluid temperature. The second one is parameter R naught can be easily influenced or dominated by internal heat sources. This result is also equivalent to the outcome to be considered M naught by Hisham 2001. And the third one is the internal heat source contributes to the increase in the temperature of the fluid area, which causes the system to become unstable. And the last one is, this study also found that the effect of gravity affects the phenomenon of oscillation. That's all from me. Thank you.